Good afternoon, everyone. I'm Leo. This afternoon, we're going to be doing. I'm going to be going over the basics of binary exploitation, also known as PWN, within CTFs. Now, binary exploitation is probably, I'd say, one of the more difficult categories, and one that I, personally struggled with a fair bit. I think I recall last week, during last week's workshop, I made a promise to Marush that I would give a workshop on binary exploitation at some point in the year. Turns out it was going to be exactly 7 days from then. So there is a non-trivial chance I'll just bollocks this entire thing up, and if I were a betting man, I would put a significant amount of money on the fact that Marish will have to give me a lot of corrections throughout this afternoon's workshop. But that being said, I'm trying to be optimistic. Let's get started on this. So the first CTF, so I've released all the challenges so people can go to them. We're going to be working on 2 different sets of challenges. The first are the first 3 challenges from Narnia OverTheWire, and then 2 challenges which I just made this afternoon, or one I made a few months ago, one I made this afternoon. So Narnia 0 is Narnia is one of the categories of challenges within OverTheWire. Now, if you go to overthewire.org, they've got a series of challenges there. I think Narnia is the binary exploitation category, but they've also got, Bandit for web. Actually, no, Bandit is Linux skills. I believe there are Natus is web. There are all kinds of different categories. We'll be going over the binary exploitation category. You can either go to OverTheWire, or I've given connection instructions on the description here. So to connect to this, you need to use SSH. If you're on a Linux or Mac or any kind of Unix-based operating system, you can do this. If you're on Windows, you can either install PuTTY or install the Windows Linux subsystem, which is what I'd recommend. And so once you open up, you can just connect to Narnia OverTheWire, and Narnia 0 at narnia.labs.overthewire.org, and then specify port 2226. And in the first challenge, the password to connect is just the phrase Narnia 0. However, every time you solve a challenge in Narnia, the flag you get at the end of it is the password to connect to the next one, and so you need to do them in sequential order. And so once you're in here, the instructions are on the description of the CTF platform. However, if you navigate to the root/Narnia file, then you will see a series of. Actually, I'll make that a bit bigger. Hang on. Yeah. And you'll see a series of files here, Narnia 0, Narnia 0.c. Now, you can only actually read or execute any of the challenges according to which person you're logged in as. And so in this case, you can only execute Narnia 0 and read Narnia 0.c. Now, the format of this is that if you can print the source code of Narnia 0.c, and it will give you a program in C. What it does is it sets this value here. It's initially set to val, which is hex 41414141, which some of you might recognise as being, I believe, just the letter A in ASCII repeated, and then it gives you a buffer of 20 characters. And then one thing you might notice here is that scanf is prompting you to read 24 bytes from the user's from standard input. However, the buffer is only 20 bytes, implying that there is a possibility of a buffer overflow occurring here. Now, what a buffer overflow is when you've got a buffer and you overflow it, basically. So essentially, taking in more input than the program then the program has been designed to handle. And so I think the best way to describe how buffer overflows work is just to give a general overview of the memory map in C and show how it works. So generally, has anyone here done FIT 1008s or done MIPS or? Because if you've done any of those kinds of subjects, you should have a vague understanding of what a stack frame is and what a memory model is. So basically, every single time you actually, just to make things clearer, this program, the first Narnia challenge has quite a bit to it. Like it's got different jumps and comparisons and calls different functions. But I'm just going to make a very simple version of this challenge just to demonstrate how assembly listings work and how they compare to C. Let's say I've got a program, say int main, that calls a function called vuln. Now, because often the entry point of the program has a weird stack frame setup, it's often better to have vulnerable functions be called from it. And so let's say you've got this function vuln that doesn't return anything. And the format here is that it's got a char buffer. Let's say there's a value. There's a value here that you want to change. I'll call that long val equals 0x 4, 1, 4, 1, 4, 1, 4, 1, which is what it is in the Narnia challenge. I'm excluding all the other comparisons in it, and then you've got a buffer, char, buff. Let's say it's got 8 characters in it. I'm just simplifying things a bit. Now, generally, the way this works, to check how the memory layout of this works, it's probably better to actually draw a stack frame and see how things are laid out. Now, when main calls vol, the first thing it does is, let's just say we start with a stack frame. Let's just say it's completely empty. In practice, there's going to be stack frames of previous functions underneath. Let's just say the first thing it does push EBP, move EBP ESP, which basically just sets the current stack frame, sets the base pointer to the current stack pointer, which basically says, okay, I'm going to set the register EBP here. Actually, I should probably mention, I'm probably jumping a bit too fast. So we're using x86 assembly, which is a 32, which is Intel's x32-bit instruction set architecture. And so in x86, there's a series of, there are these general registers, EAX, all other ones, but then the ones we care about the most are EBX, which points to the base of the stack, and then a stack pointer, which points to the top of the stack. Now, if you've taken an algorithms class, you'll know that a stack is a last in, last out data structure. So so to add more stuff to the stack, what you do is in this case, you would, so when you start here, the stack pointer, or pointed to by ESP, is going to be pointing to the bottom here. However, at the function prologue, at the very start of the function, what it will do is it will decrement the stack pointer and to make space for all of the local variables. Now, underneath the base pointer, it will store the return address, and it will also store all the all the arguments being passed to that function. However, as you can see here, there are no arguments being passed to it, and so we can just ignore that. And so here we can tell that the first thing to do is push EBP, move EBP. I won't go over the entire function prologue, but the things we care about when it says sub ESP 24, which in this format it means subtract 24 from ESP, then store the result back in ESP. So basically, set ESP here, which is a difference of 24 bytes total. And the reason we have 24 bytes here is because the value of val, now val is a long integer which has 8 bytes by default. And so generally speaking, the way it works here is that we can say this value here, let's just say here is the value EBP minus 20. So basically 20 bytes up this way. So the way it works is this bit here is the buffer, and this bit here is the value val. And because in here it's doing, let's say getS buff. Now, getS is a vulnerable function in C, meaning that it will just take input and will just continue reading input for as long as you want, overriding any buffer you want. So let's say, what do you think would happen if we were to write more characters than 8 into here? As you can probably tell, it would start overflowing into the val function, into the piece of memory that stores val. And so the first challenge here in Narnia 0 is to do exactly that, to change the value. Peter, do you know how to the laptop back to here? Primary stream. Cheers. And so what we need to do here is we've got this value here, we've got a buffer here that we want to overwrite and set to val. And as you can tell here, it's reading 24 bytes into a buffer designed for 20 bytes, and there is a 4-byte variable here. So as you can probably tell, you just need to write 24 bytes with the last 4 bytes being the hex value dead beef. Now in this case, if you set dead beef to it, the hex value that is, then you will get you'll be able to get the flag. So the first thing you might want to try and do is this challenge is quite forgiving in that it will. It's cutting out a bit. Yeah, so if you run it, it will tell you exactly what the value is overwritten to, so you can make corrections. Let's say, let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'll just set this amount to it, and it'll say, actually, let me just run it without doing anything. So in this case, I'll send 4 bytes, and the value here is completely unchanged, as you would expect. But if we were to run this by sending more than 20 bytes, then as you can tell here, the value has been set to hex 666, or the hex 6 reoccurring for that amount of bytes. So if you check the value of the ASCII value of hex 66, that is just the ASCII entry for F. And so as you can tell here, these last 4 bytes here have been set to value, but value's been set to these last 4 bytes here. So what we want to do now is set it to this value here. And the best way to do that is just use, to use Python and just print those values here. So let's say we know that the offset to value is going to be 20 bytes. So let's just say I'll print A 20 times. And now what we want to do is we want to print the raw bytes of dead beef. We don't like the actual. This isn't like an ASCII string, with the ASCII character for D, then the ASCII character for E. This is like literally the hex string that in base 16 it spells DEADBEEF. And so we can do this by printing the hex value. So let's say we'll do hex DE, BE. And can anyone tell me what they think will happen when I run this? I think Mariusz already knows. I recall he did the exact same thing during his workshop last year. But if you run this, if you actually pipe it into Narnia, then it will say, actually, what have I done here? Did I actually print this? Hang on. Yep, so this still works. Sorry, I don't know what I did wrong there. So what I want to do is I want to print just a base of 20 characters, and then print just 4, and then just print some bytes afterwards, just to check that I actually can override it to whatever value I want. Yeah, does that actually work? Oh no, I didn't actually print it. Shit, hang on, that makes sense. Yeah, the print statement makes all the difference. Yep, so if I do that, pipe it into Narnia 0, and it will say, it said, so I've overwritten it, but you can tell here that the value, instead of being set to hex dead beef, has been set to hex EF, BE, AD, DE, which seems like the right characters, but it's ordered in a really weird fashion. Can I get a show of hands if anyone knows why that's occurring? No. Great, someone's responsive. So this is because of endianness. Specifically, you can tell just from typing LSCPU, you can tell here that the byte order in this CPU is little endian, meaning that in each word, so in each chunk of 32 bytes in a row, all the bytes are stored in reverse. So in each chunk of 8 bytes, the bytes are stored in the reverse order. So if you want to do this, what we have to do is actually print. Now, keeping in mind that 2 hexadecimal characters next to each other makes exactly 1 byte, what we can do is we can go back and print. We've got to do it in reverse order. So the last 2 bytes are EF, BE, AD, DE. And that worked. So I've set it to dead beef. Now, the annoying thing about that in Narnia 2, like I think I gave a hint in the description of the challenge, but if anyone's gotten stuck on this, what you can do is actually get the persistent shell. You've got to actually put it in brackets here, and then also type the command cat just to make the shell persistent. So now, now I should have a shell. If I type who am I, then I've logged into the next user into the next challenge because of the set UID bit of this challenge. Does anyone have any questions? Is anyone working on this at the moment? Anyone on Zoom? Right. So now in this case, you can stay in this shell to attack the next challenge, but what I find is easiest is just to cat etc/Narnia pass/Narnia1 to get the password. And this is actually the flag of the Narnia 0 challenge if anyone wants to submit it. I won't keep it on the screen for too long just to make sure people actually solve it themselves. And so any questions at all? Yeah, that should work. Now, the Narnia 1 to 2, now the Narnia 1 and Narnia 2 are a bit more complicated, and so as a quick interlude from that, I'm going to go into this challenge, Call Me, which is a slightly more middle-grounded challenge. Now, this challenge is the sort of a very typical challenge you'd see in a CTF. It's not as common to have SSH into boxes to do these pwn challenges. The most common format you will have is they will give you an IP address and a port to send your raw bytes to, which is most easily communicated over netcat, this program here, NC. And they will give you these two files. They'll give you the binary. In some cases, they will give you the actual source code in C. Now, the Bank of MonSec and the Call Me challenge here are both solvable without actually reading the C source code, but they're included there in case anyone is not very familiar with assembly. And I'll probably go over the source code quickly just to show how this works. So the first thing to keep in mind, the first thing you can do is once you connect to the service here, it's just it gives you the prompt, welcome to the flag sharing service, please log in to continue. You enter a login and it says, sorry, wrong user, better luck next time. And you can also download the file and look at that. I'll just download these to have a look at. Yep. Oops. So now I'll just have a quick look at the callme.c source code. Oops, no, that's the wrong one. And so here you can see there are three functions. The first function is in main, the entry point that says, welcome to the flag sharing service, log in. It calls login function, then says the wrong user. But the interesting thing here is that you can see that this function here, getFlag, which just types cat flag.txt. And so basically to win this challenge, you need to get the system to run this function. However, one thing you will notice is that there is actually no call to this function at any point in the system. And so you might think, well, how is this function ever going to run if it doesn't actually get called? But go back to the actual stack frame layout that I mentioned earlier. Now recall here that the current stack frame is all the values between the base pointer and the stack pointer in the current function being executed. And underneath is the return address, so the saved value of EIP, which is the register that stores the current instruction being executed, and then underneath are all the arguments being passed. Now keep in mind that if you've got a buffer that you can write to here and go down, now think to yourself, what would happen if I could go down further and overwrite all of the values underneath the stack frame? Now keep in mind that the prologue, I forgot the name of it, but the thing that the function the assembly listing that the function does before it exits, it will pop the value from, it will set the stack pointer to the current base pointer, basically just clearing the entire stack, leaving the saved instruction pointer at the very top of the stack. Then it will execute pop EBP, meaning that it will take the saved, it'll do pop EI. So basically it'll do a return instruction, which is just setting the current instruction pointer to EIP and then resume execution at that point. And so you're probably thinking, if I can actually overwrite the buffer here and then overwrite the saved instruction pointer, then I can control whereabouts this function jumps to after it finishes executing. And so the way that you do this is by actually finding the address of this function or the offset in the binary and then replacing that and replacing the saved instruction pointer with that. Now to do this, you can't just, it makes a lot more sense to actually use a proper debugger instead of just, you can't just do it blind like the Narnia 1 challenge will let you do. And so now the tool that you'd probably most likely be using is a tool called GDB, or the GNU debugger. Now I'm using pwn.gdb. Hello? Yep, this just keeps cutting out every now and sorry. So the plugin I'm using is called pwn.gdb, just makes it a bit easier, but you can do, I'm not going to use any features in here that are too complicated. And so the way it works is you can actually look at the disassembly listing for each of the functions. If you go disassemble main, it'll look at all the assembly listings. Like, here's the, if you want to go to, the function we care about is login. So, how long is it like that? Can you speak up if I do that again? Oh, great. Anyway, so thanks. So anyway, the current, well, I didn't actually do anything really that much then, so it doesn't really matter. But basically, you can type a disassemble and then the name of the function if you want to disassemble it. And so the current function I'm looking at is login. Now, as I mentioned earlier, here is the function prolog push ebx sub esp -20. So basically, set the base pointer to the current stack pointer and then subtract from the stack pointer to make room for the current stack frame for all the local variables. And keep in mind that before the function is called, the caller of that function will first put the arguments and then the return address of the function of the current instruction pointer on top of it. So it resides just underneath the base pointer. And what you can do in GDB, you can set breakpoints and then have code stop there. So what I want to do is I want to have the breakpoint that calls. I want to have a breakpoint that is. Actually, let's just see what happens without doing anything fancy. I'll set a breakpoint, so I'll do break, and then login plus 45, which is the last line of, which is the second last line before the login function actually returns. So I set that breakpoint there and then run. It will execute. It will prompt. What do I do now? Oh, oops. I know what I did wrong. Little search mod. Yep. So if I do break login plus 45, then I can now run this function and it will, this program, it'll ask me to prompt my name, username, and then it will call a breakpoint. So it will tell me the state of the current registers, the disassembly of the lines being currently executed, and the values on the stack and the current backtrace. So as we said, this function was called by main, which was called by the libc entry point. And so what we can do is we can look at the current state of the stack frame. We can do info frame, and it will tell us what the current instruction pointer is. And if we do disassemble login again, you can tell that it's got this arrow here to tell us which instruction we are currently looking at, which is the value of the current EIP or instruction pointer. And the saved EIP is the one we care about. The saved EIP is the instruction point, was the area in memory that the function will return to after login is completed. So if we now disassemble main, you will notice that this value here, saved EIP hex 8048553, is the line of code directly after the call to login. And so what this means is that after login finishes returning, it will return to this bit here. But what we can do is we can just overwrite this value to make it return to any arbitrary place in code. So what we can do here, I'll just run it again, and I'll just enter a ton of A's, like way more than the program is meant to handle, because the program's only meant to handle 10 and I'm putting in about 50. So if I'll do that, now if we look at info frame, the saved EIP is hex 61616161, and hex 61 is the ASCII character code for the letter A. And what that implies is that the letter A's have just gone. Oops. Shit. What this implies is that the A's have just gone all the way down, and now the saved instruction pointer is just the letter A repeated. And so, as you can expect, if we continue, we will just get a segmentation fault because it has tried to jump to a very invalid piece of memory. But now what we need to do is we need to find the actual address in memory of the getFlag function. So what we can do here, there are a lot of, you can do this in GDB. I like to use the program object dump, obj dump -s call me. Now it'll show you all of the different addresses here. And I'll make this a bit smaller. So for example, here's the different functions, libc functions, main, that's the address of the main function, the address of the login function, and the address of the getFlag function. And you can also get this in GDB through info functions. But that lists quite a lot. We don't really care about half of them. And actually, no, you can see it on here as well. So I'll just copy that. And so what we need to do is we need to find the offset Like, for example, we need to find exactly how many characters we need to write in here before we start writing into an instruction pointer. And so the simplest way, you can do this manually by just typing all kinds of different combinations to see which offset you get, but PwnGDB comes with a tool called Cyclic, which there are online tools to do this. You can do this 100 different ways, but with Pwn tools and PwnGDB, you can just do Cyclic, say 50. I'll do 80. And it'll give you some repeating characters here. And so what we can do is we can just run it again, and we can enter our username as this. And if we continue to our breakpoint, you can definitely see our characters have overwritten the stack here. But if we do info frame, then you can see our saved EIP are these values, hex 61, 67, 61, 61. And what this cyclic pattern finder will do, it can tell you how it can look at that pattern, that series of 4 characters, and tell you exactly how far along in the sequence it is. And so if we do cyclic -L and then 61, 67, 61, 61, it'll tell you, okay, that is exactly 22 characters in. So let's just do a quick test here. Now, one piece of syntax you can use to run with a certain input in GDB, which is the equivalent of piping input into the program, you can do run these characters here, then to do Python 2-C. Now, it's good to use Python 2 in these scenarios because if you try to print a byte string in Python 3, it will format it and will literally print B apostrophe, then all the characters, and we want the actual raw bytes to be printed here. So you can Python 2-C print A times 22 because we know there's an offset of 22 until the saved instruction pointer, and then plus, and then let's just write, dead beef again just to make sure we actually have some value we can write to. Now, if we do this, hopefully, yep, the saved instruction pointer is dead beef. So that's just a simple proof of concept to check that we can set the instruction pointer, the saved instruction pointer, to be exactly what we want it to be. So now that we've got the actual, address, we can just have to write that in. Now, one thing I like to use is that PwnTools has a tool called. Now, just because correcting for little endianness gets a bit tiring after a while, I like to use the function p32, which will oops, that's the wrong one. So yeah, so what I like to do is I like to get the address of getFlag, put it into p32, and that will format it in little endian bytes automatically. Just saves me a bit of time. So what I can do is I can copy that and then run the exploit again, and hopefully I should jump to, yep, run here, info, yep, that's the one I want. If I continue now, this will cause an error because it'll say cat flag.txt, no such file. But now what I can do is if I just run this, if I just run this and pipe it into netcat, then hopefully I should just get the flag like that. Yeah, and there is the flag. Now, this can be a bit, confusing if this is an area of, this is a topic you're not very familiar with. So does anyone have any questions at all? Is anyone in Zoom saying anything? Are people working on this at all? Because if I'm going too fast, I don't want to confuse people or leave people in the, or maybe I'm not going fast enough. I don't know. I'm not great at pacing. We'll find out. So if that should work. So what challenges are people working on if they are doing anything? Whatever. Also, actually, yeah, I will take this time to mention, because I forgot to mention at the start, MonSec is still currently looking for general representatives, and so we are still recruiting, and the application to that will be open until the end of the week, I believe. Friday, yes. And additionally, one other thing is that our CTF team, our competitive team, did a CTF on the weekend, and it went quite well. I think we came 15th out of how many? Do you know? Yeah, 15th out of over 1,000. We did very well. I think I'm very proud of how we did. And so I know I've said this quite a few times that if anyone here would like to compete in the would like to be in the competitive team with us, we'd be more than happy to have you. And you just need to DM your student ID to one of us to get confirmed to stop other teams from joining and stealing the flags from us, which I did try to do to Melbourne Uni once and I got kicked out. That's a story for another time. All right. Now, if people generally understand the concepts of how stack frame layouts work and they can understand, the significance of being able to jump to arbitrary areas of memory, then in that case we can probably move on to Narnia 1. Now, Narnia 1 is where it starts to get interesting. What was the flag for Narnia 1 again? If I just scroll up, I should probably be able to find it. Hang on. Actually, I can probably just get it from here. There's nothing confidential on here, is there? Yeah, maybe it is. Yeah, there we go. That's not cheating, it's gaining a tactical advantage through deceit. So, one at start over the wire. And using the password of the last challenge, because that still has to be sequential, paste that in. Now, Narnia 1 is where it starts to get interesting. The first one was a bit of an introduction to the field for people that aren't familiar, that just to know what it means to actually overflow a buffer, but this is where, it gets interesting. So again, I'll go to Narnia, and I'll have a look at the Narnia 1 source code. Oops, why can't I? Now this challenge is where, can anyone, just looking at this challenge, can anyone figure out what the best way to approach this is? Just, just someone yell out or throw up their hand or something. I just want to see if anyone can guess what they're supposed to do in this situation. Yeah?
You might want to set egg to something before you run the binary.
Yeah, that is what you do. Can you guess what you have to set egg to? What you have to set this variable to? Not quite. So what this is, so in C, what this is declaring a function pointer to a function that returns an integer, and then it will look at the getEnd. It will look to see if you've set a variable called egg in your environment, and if you haven't, it'll exit, and otherwise it will basically execute the instructions stored in there. And so this challenge is what is known as a shellcode injection challenge. Now the benefits, I think in a lot of CTFs, you'll find that return-oriented stuff can be a lot more powerful, because in all the situations where you can do shellcode injection, you also can do return-oriented stuff. But in this case, Narnia specifically designed this for shellcode, because it is literally jumping to whatever code you write. And this is a situation that never really presents itself. So let's say I'm going to set a variable to, say, some letters. Export egg equals A, B, C, D, E, F, G. Yep. Now can anyone guess what will happen when I run this? Yep. It'll segfault. And the reason is, if I run this, then it'll segfault. And if I look at the frame, hang on, IP, what happened is, so you can tell that the instruction pointer is currently set to B, C, D, E, F, and because I set this to A, B, C, D, E, F, what that means is basically, it looked at the character, it looked at the instruction encoded by A, tried to execute that didn't work, it skipped to the next one, and so it self-faulted because it didn't know what to do there. And so what we need to do is we need to find some valid code to actually have a jump to that can do something. Yeah. Does anyone know how they go about doing that? Right, so you can, if you want, you can compile your own code and get the raw bytes of it from it yourself. A lot of people do that. There are tools for doing that, but the easiest way in this case is to go to Shellstorm. Actually, if you just Google shellcode, there's this comes up. You can go to Shellstorm. It's basically a giant database of all these different pieces of shellcode you can use. Now in this case, you want to find out which one supports it. You can just type some stuff like, so we know it's got to be it can be a 32 or 64-bit shellcode. Yeah, so basically, now the annoying thing here is that in some cases it takes a bit of trial and error, because you have to go through and try and find some shellcode just doesn't work, and it's a bit hard to tell why it doesn't work. I'll save you the trial and error, but because the piece of shellcode I found that worked was, if you go to any piece of shellcode, It's the one number 756. Yep. And in this case, what this is the raw bytes of an assembly. So it's basically assembly code actually converted into the raw bytes that the CPU executes. That will, and in this case, what this will do is this will run the code execve bin/dash, which I believe is symlinked to bin/bash, I think. So basically, you get a shell into the system. And so once you actually get that code and clean it up a little bit, it's a bit annoying that it's formatted a bit weirdly, because I think they're intending for you to just paste it into a C document. And so what you want to do here is just set an environment variable to the raw bytes of this shellcode, and then the program will then jump to that code and will then get that code and start executing it. So one on here, you can just do export egg equals this, and that will work. But can anyone tell me what the problem here is, or whether this will work or not? So one thing you might keep in mind, that if you wanted to echo egg, it's just printing the raw bytes of this. And so you can tell if you pipe it into XXD, it is formatted properly, it's not raw bytes. And so what you want to do is, there's a few ways of doing this, but the way I like to do this is to use backticks, which means that it will execute the code in between and have it print these raw bytes. Oops, no, I didn't actually. Does that work? Oh no, that's echo, not export. Export egg equals Python. What do I do here? These demos never work on stage. I did this about 100 times before I came here. Oh no, that's you don't have the actual $sign there, I forgot. If I export egg equals this, then pipe into XXD, and that will be the right, yep, EB18, yep, that's the right bytes. And so now if I just execute Narnia 1, yep, that'll execute a shell. But because of the setuid bit of this program, then that shell is an elevated user. So I'm now, if I type who am I, I'm now currently executing as Narnia 2. And so again, I can just cat the password file, etc/passwd, so no, etc/muscle memory there, pass/Narnia 2, and that is the flag for that one. Any questions at all? Was anyone stuck on anything? Yeah. Is anyone working on this at the moment? Well, I don't have to ask. I can just find out, or at the very least, I can find out if people are successful. Yeah. So many people have solved this one. Oh, it's got 13 solves. Very well, very nicely done. Hopefully, you didn't all just copy the flag from my screen. Very nicely done. And no, and I'm the only one that's gotten this one so far. So in that case, I might just take a quick break and let people work on this, and then I'll come back and give a quick demo of the other challenges if people still want to see them, or if people get stuck on them. Is that right? Are there any questions on Zoom?
There's a question about the recordings.
Yeah.
So yeah, you just say that we've got a backlog of a few recordings.
Yeah, actually, yeah, just to mention that, we have been recording all of our workshops, but I think a few of the committee members are human and therefore failable, in the sense that we just haven't gotten around to uploading the last workshop. I've been busy recently. However, that we have physically got the file for it, so if any of you couldn't make it or will be attending or would like to watch the workshops later, they will be uploaded very soon. I believe the workshop from 2 weeks ago is uploaded. However, the cross-site scripting workshop from last week is yet to be uploaded at the moment. Yeah, and also for anyone that wants to do these challenges later, or for anyone that's currently watching this video recorded a week from now, hi from the past, but also these two challenges, Call Me and Bank of MonSec, will probably be only running for at most another day or two. And so if you want to attempt these challenges, I would suggest you have a go at them sooner rather than later. This definitely isn't the last you would have seen of the challenges, but I'm running it myself, so I don't want to pay too much for it. Any questions? All right, I'll just go around, see how people are doing, let people work on stuff, and then maybe come back and do the last two challenges if people still want to. Now, in my opinion, Narnia 2 is where it starts to get interesting. You start to see some proper shellcode. Is that right? Yep. So, yep. So I'll have a look at So just stop myself from having to go back and solve every one in a row. I'm just going to copy the flag from there. I know this is kind of cheating because you guys can't do this, but you're more than welcome to keep logs of flags as you go along. Narnia 1 to 2. Yep. All right, so in my opinion, this is, I said it again, but this is the first proper shellcode you get because, in the wild, you're never going to see people just executing random environment variable set in that session. So, this is where you're going to see something proper. Now, in this case, I often like to have two terminals open and connected to the server just so you can actually write files while you're write files and execute them instead of doing them all as one-liners. You can get away with doing, Python 2-C when you're doing more simple programs, but in this case, it's good to actually have a proper file you're working on. Okay, so this one here, Narnia 2. Hang on, I'll make this a bit bigger for you. Now, Narnia 2.c is interesting. First, it gives you a 128-byte buffer, and what it does is it will use strpy to copy the first argument you provide to that buffer and will print that buffer. So for example, if I do Narnia 2, it'll say usage none because I didn't specify an argument, so argc is equal to 1. I'll do Narnia 1 test, it will print that, test, Shen. Now it's not actually formatting it, so it should be actually no. So if I just do Narnia, if I specify a whole bunch of A's, then it should just print all those A's. Yeah, actually, no, I'm going to give you a segmentation fault because once again, I overrode the stack frame. Now, has anyone got any hints, any ideas what they think this challenge involves? Well, I already Shellcode, but does anyone know what they're going to be doing in this challenge? You're a genius, great. It involves a buffer overflow. So, hang on, what have I got written here? Once again, because I know, I could do this, but because it's a rule of nature, as I mentioned before, that these demos never work live. I've just got what notes I'm working from, and so what you want to do is you want to actually, once again, you need to find the offset to overwrite the return address because that's usually the first thing you want to do. Now, because I'm doing this on their server instead of my own, it doesn't got HomeGDB installed, so I'm using vanilla GDB, which should still be fine. Here I'm just setting the assembly flavor to Intel to make it Intel instead of AT&T syntax, which is just a lot nicer to read. And so as you can see here, it's just got the main function here, and it's copying all this. But what we care about is knowing how many characters here we have to use until we overwrite the buffer. Now, because we haven't got it on here, what I like to do is just have my own thing here. You don't have to use these tools. As I mentioned before, there are online tools you can use, or you can just use any tool you want. So I'll just do, g.get, say 200, because it's a rather large buffer, and I want as much as I can. So what I'll do here is I will run this so let's check what happens if I run this program. So and then I specify this rather large string here. As I expected, I'll get a segmentation fault, but I need to find exactly at what point it is writing to the saved return address. So again, I'll run it with GDB. And I'll set a breakpoint near to main plus 81. So now I'll just run it with that giant argv1. And if I do info frame, it should say EIP is hex 62616169. So if I do g.find, we do it here, I should get the offset as 132. So in that case, it's, position 132 in chunk 132 with an offset of 0. And so we know that if we do, say, if you do run it with, actually, no, I'm just going to make a quick temp file, tmp/monsec.py. And so if we just do yep. So this mic keeps cutting out for a bit. A times 132. We want to say print base, which is reach the offset. So print base plus P32. I'll do dead beef again. Just because that's easily recognizable. So if I run this with Python 2, then as I can see here, the saved instruction pointer is hex dead beef. But now what? There's no function we can return to that will immediately give us the flag. And so, as I think I mentioned before, you have to use shellcode. But instead of just having a shellcode that is loaded and executed by a function pointer that the program declares and picks up an environment variable, you need to actually write the shellcode to the file yourself. And in this case, you're doing it by writing it to the buffer. Because here, as you can tell, there's a rather large buffer that should be enough for any shellcode. Another thing you can do here, look at, is this loaded? So if you have a look at this, now Pwn Tools comes with a tool called checksec. And it will run it, and it will check the thing. So here you can see there is no stack canary, meaning that it's very easy to clubber the stack and just write as much as you want. And most importantly, the NX bit is not set. And the NX bit is redux or write, which basically means it makes the stack executable. And so whatever you write to the stack, it is possible to jump to that code on the stack. And so what we need to do here is just write the shellcode somewhere onto the stack, and then using the values of the stack pointer we know, just set the return address to some value on the stack so that it will jump to that code on the stack and then execute it. And so once again, now that we found the offset, this should be fairly easy to, well, somewhat easy to do. Now I'll just copy some shellcode from here. Now the shellcode I found, now once again, trial and error, but I'll just save the time. The shellcode I found that worked with this was shellcode 811.php, which does the same thing, exec ve bin sh, which is only 28 bytes, so it's quite small. Now I'm just going to copy a whole bunch of different things here. So this is, oops. So I'll just save a whole bunch of these variables. So I'll say, I don't know. Let's just say shellcode equals B, and then the shellcode we've got. Now, the best way, now what we can do here is we can actually, now I'll run the same things we had before. Plus 81. Now, if I run this, actually, I'll run this with a large value, but not one that's big enough to clobber the stack. I'll run that. Info frame, and the stack address hasn't been overwritten. But one thing you can do is you can print values from the top of the stack. So one thing we'll do is we'll do x/150x ESP, which means find the first 130 words, which are 32 bits. 32 bits information from writing down from the stack pointer and print them all. So if I print them, then you should get at the top of the stack, as you can see here, hex 61, 62. That's A, B, C, D, over to the end, and then you should find somewhere down the stack the value of F7 E2. I'm pretty sure this is the return address here, but if we don't know that, we can figure that out ourselves. So what we can do is we need to find a base to. Best way to actually jump to this is to say, well, let's just verify that this works at all. So let's just say, now there are two instructions that are very handy to keep in mind. Now the first is the x86 instruction int3, which is just equal to the byte hex cc. Now the byte hex cc is just an interrupt. It halts the execution of the program. Fun fact: the debugger in here works using the hex cc thing. So if you set a breakpoint at a certain offset, what it will do is it will find the instruction stored to that thing and replace it with hex cc. And so by putting this byte in shellcode at any point, we'll just hold execution. And it's just a good way of testing. So shellcode and it stops running, that means you've got remote code execution, and that should work. Another one to keep in mind is the one called NOP, which is just equal to hex 90. And NOP stands for no op. It just means do absolutely nothing, and we use them in something called a NOP sled, which I'll cover shortly. So what we want to do is we want to inject the shellcode at some point on the stack, and then overwrite the saved return address with one of the values here. And so we can do this by saying, let's just debug this first. Let's say print int times 132. So that should be the same as the offset. And then plus, let's just say, get the top value of the stack here, and then print p32. I'll just correct the endiness here. And then print this address here. I don't think it actually matters whether you put the -x, the B at the start there. So if you write that there, I should be able to do and hopefully, yep, the saved return address is this point on the stack, FFFF D618, and if I print the stack, D618, that's part of that is this point here. But as you can tell, it's not at the very start like it was before. And so if we actually were to continue with this, with the C, received signal sig trap, trace breakpoint trap, which means that our instruction int has been reached and executed. And so now, but the thing is though, I don't believe that this challenge uses, now this challenge doesn't have ASLR. Now ASLR is a thing that means that the stack has random offsets at the start of it. This Narnia hasn't disabled, but one thing that you got to keep in mind is that occasionally when you run things on GDB and then off GDB, there will be slightly different stack values still, just because I believe environment variables and other stuff present. And so what you can do is you can put a whole bunch of NOPs at the front to make something called a NOP sled, which basically means that if you put, like for example, let's say you put the shellcode right here. Now let's say your address was slightly off, and so you hit the shellcode here and started executing. Now that would change things completely, because you're just skipping random instructions and not executing things, and so naturally your shellcode wouldn't work. But if you put, say, a whole bunch of NOP bytes here, it doesn't matter whether you hit it here or hit it here, it will just hit that and keep executing, doing nothing until it reaches the actual shellcode. And so it just gives you it just gives you a lot more leeway and a lot more freedom with regards to that. And so the best way I found to do this was to get the shellcode, and now what we got is we need 136 bytes of padding before the thing is overwritten. So what we can do there is we can about 107 bytes of a NOP sled followed by the shellcode, because the shellcode is 25 bytes. And then after the shellcode, we have the address on the stack to jump to. And so hopefully if we execute that, then it should jump to some point in the stack, hit the NOP sled, go through, execute the shellcode, and we'll get our password. And so if we just do, print NOP times 107, so our NOP sled, because it's 107 plus 25 is 130, hang on. Yep, so 135, so 107, and then plus the shellcode, plus our address. Now the address we care about is, let's just say, this address here. And so let's say P32, and we'll copy this address here, having formatted it for endianness, plus this. Now hopefully, if we were to run this now and continue, got a seg fault. What happened there? Look, sometimes it runs different in GDB. I'll just try running it normally. Segmentation fault, great, what happened here? FFD8, 50, oh, hang on, I'll try the actual address here. Now, sometimes, shellcode can be a bit finicky to set up, and so you can just spend the time messing around with addresses and stuff. D8, and again, I'm not an expert on this, but hopefully I got another seg fault. Now I'm just going to actually verify that this is doing anything. So instead of printing that, I'm just going to check that I can actually print anything. So I'll print. Because what I want to know here is whether it's missing the shellcode entirely, or whether it is hitting the shellcode halfway in, or if I've got my addresses wrong. So I'll just say print int times 107, so basically replacing the NOP sled with the shellcode. And hopefully, hang on. This worked just before I came in. I don't know what's happening now, to be honest. Yep, shellcode is an absolute nightmare to debug, I'm afraid. Sometimes it works, sometimes it doesn't, and you never know half the time. But actually, no. I'll tell you what I will do. I'll do it with GDB. So what I will do, I'll get it to print the shellcode with the NOP sled, then set a breakpoint and check to see whereabouts it's jumping to. Hopefully, I'll figure out what my issue is there. None of this is scripted, by the way. Just want to let you know, shellcode is just annoying to debug, and this is half your problem all the time. So if I run, oh, that's right. Yeah, I do need a breakpoint. I forgot. Plus 81, I believe it was. Oh, no. So I'm here at the end here. Now if I do info frame, the save, hang on, EIP is, that doesn't look right. Yeah, I think I might have CD 40, like, previous. So we've got our NOP sled here, followed by our thing 319. Hang on. Do you know what's going on here? I'm at a loss. This worked 10 minutes before I came in here.
Is the shellcode 25 bytes long?
You know, I'll do this in terms. I'm going to do this in terms of actually calculating lengths instead of relying on the... Actually, yeah, I'll tell you what, I'll just do it manually. So I'll do... No. Yeah. I can't remember the bloody single step versus different step instructions. EIP is... And this is going to segfault, I guarantee it. Yep. Look, I'm just going to try one more thing, and I'll probably give it a break because this is infuriating. Sorry?
Look at the
Saved EIP. FFFF D640. D6. What's happening here? Yeah, all right. Mara will be doing the workshop on ROP next week. Hang on. So I'll just print NOP times 132 minus length of the shellcode plus, and I'll do a quick offset off here, plus 8. Actually, I'll just do it here because it shouldn't matter if it's NOP. And if I'm not insane, this should work. And yes, this is as fun as it looks. Hang on, F's what? Hang on. Okay, actually, give me a second. All right, you know what, I'm going to give this a quick break and because I think I'm going insane up here. I don't know why this isn't working, but hopefully I've managed to explain the concept at least to you. Because the concept is you want to find the address on the top of the stack, put the shellcode at some point in the stack, put a NOP sled at some point before it, so it doesn't matter exactly where you jump to, and then jump to that point on it. All right, so that was a great success. I'm going to leave it at that for now.